Correct. So what we discussed last time are we didn't actually finish the applications of possible applications of groups. So I think we were discussing applications to mathematics, right? So lecture number 2, applications to mathematics. We're discussing applications to topology and differential geometry, right? And I'm just going to quickly review what I said last time in this topic. So in topology, I said that there are these groups called the homotopic groups. And I think they were introduced in mathematics by Hopf. And homotopic groups are essentially maps from the n sphere into some space. It can be some shape. It doesn't have to be exactly a manifold, but yeah. So these are topological invariants, these groups. And what are they? They're equivalence classes of maps. So for example, suppose we have some space, say M, such that it has a hole in it. So the thing in the middle is not part of the space, okay? And you are looking at all the maps from, say, S1 into this space, okay? And that group is going to be called pi1. So there, you can have all possible embeddings of S1 in this space, right? So, for example, this one. Now, the thing is that this embedding of S1, this first embedding of S1 and the second embedding of S1 are homotopic to each other because you can continuously deform one to the other. So they will form one element in the homotopic group, and they will actually form the identity element of the homotopic group. You might say, what is a group action? The group action is basically going to be composing circles. Okay, so if this is an element, and then if they so essentially the composition of these two elements is the composition. But see that there are embeddings of the circle in the space which are, say, going around the hole, and the blue one can never be deformed into the red ones, right? But the blue one can be deformed into, say, this one. So the blue embeddings of the circle in this space form a different equivalence class of maps. And then what if you actually go around this thing twice? Here, sorry, the autocorrect is not. So here, we are not, there's no intersection here, by the way. So then, we see that we can embed the circle in this space in such a way that the circle can go around twice once we go around once in space. So we say that that map has winding 2, a winding number of 2. And so we see that if we now give an orientation to the winding, we can have positive winding number and negative winding number. So for this particular space, qualitatively, I can say that I can label all the maps by integers. Okay, so therefore, this is going to be pi1 for this guy is going to be isomorphic to the integers, group of integers under addition. So this is kind of a neat example of group theory which measures topology. In this case, what it is measuring is that it is telling you that there is a hole in the space. So if you were to work out pi1 for a space like this, say n, then you see that there are only trivial elements. Everything can be deformed into this point. So in that case, pi1 would be just, well, I like to write 1, the identity, the trivial group. So that's going to be as an application of group theory to topology. And then we discussed about application of group theory to differential geometry. And there's one thing called the holonomic group. So the holonomic groups, what they do is that they measure curvature. So for example, if I have a sphere, and if I say take some closed loop around in the sphere, and I do a parallel propagation of a small vector around the sphere, then as I go around the loop, the vector will not come back to itself. If I carry it, parallel to itself, right? So essentially what I mean is something like this. So suppose that we have, so let me be more specific about the parallel propagation. So this is the sphere, and this is, suppose this is some triangle on the sphere. So these are all, say, I don't know, geodesics or something. And I start with a small arrow, say, no, let's just take the arrow like this. And I parallelly propagate it. What it means is that the angle that this thing makes with this curve is always constant. So I bring it here, but here I now parallelly propagate to this point. So now you see the angle is different. So it ends up like this. And now when I parallelly propagate it like this, then it ends up somewhere here, right? So we see that the vector has rotated. Now, because it's a two-sphere, the vector can at most rotate by a two-dimensional rotation, and we'll see that group is called SO2. So what we can say is that the holonomic group of the sphere is SO2. So this is this basically is measuring all the possible curvatures that the sphere can have. Now, in contrast, suppose we want to measure the holonomic group of a torus. Now, the torus, we can, a flat torus can be written, it can be expressed in this way, right? You basically take a square sheet of paper and you identify the opposite ends, right? Now, in this case, if you take, say, this is just a flat space, right? So if you take a loop, which goes around itself, it should be clear because that's what we do in flat space. If I parallelly propagate this vector along this loop, it's going to come back to itself. So for the torus, the holonomic group is actually identity, and that is telling us that the torus actually is a flat object. So this is one way of how group theory classifies. I'm being very qualitative here. I hope you don't mind. To make these concepts more rigorous within the context of a mathematics course actually takes 5 or 6 lectures at least. So I'm not going to go into that. But yeah, the holonomic group measures the curvature of a space. And then there are the symmetry groups. Okay, the symmetry groups. And what the symmetry groups do is that the symmetry groups measure the symmetry of the metric of a space. Now, in the case of this, the holonomic group of a sphere, at least intuitively, it should be clear that if we kind of, made the sphere a little bit oblong, that would actually not change the holonomic group. Okay. It'll, it might change some of the details of the path, but it won't change the holonomic group of that space. But it'll change the symmetry, right? Because here the sphere, it was symmetric, under rotation around any axis, right? But here we see the sphere is no longer symmetric under rotation around any axis, but it's symmetric under rotation on this axis. And the symmetry around the other axis have been sort of broken down to some discrete symmetry. So so essentially that means that the sphere S2, the round sphere, when we say the round sphere, what we mean is the sphere with a given kind of metric, a given way of measuring distance. And the round sphere has, it's invariant under all the rotation. So the SO3, which is the group of rotations in 3 dimensions, is the symmetric group of the round sphere. And when we do the coset construction and go to Lie groups, we will see that the sphere can actually be written as a quotient space of SO3 and 1-bit subgroups. Okay. So these are, and this has an extension. This idea has an extension in classifying the symmetries of, higher dimensional manifolds. Okay, higher dimensional, say, usually it's compact, but they're called symmetric spaces. So this is basically in one point, kind of telling you what the important applications are of group theory in mathematics. Group theory has an infinitely more number of applications in mathematics. So this is just scratching the surface. Okay, any questions so far?
So is SO2 the rotational symmetry in 2 dimensions?
No, SO2 is the rotational symmetry in 2 dimensions. Okay.
Yes, sir.
Yeah. So any other questions?